Publication in 1942 of a book titled The Modern Synthesis marks the dividing line between modern thinking about evolution, still referred to as the modern synthesis, and that of the various earlier pioneers. I was born a few years earlier in 1939, and I tend to identify more with that earlier period and to be critical of what followed. Robert Chambers' Vestiges of the Natural History of Creation that dominated Victorian thinking about evolution was in 1900 driven into obscurity by a recovery of Mendel's discoveries on the nature of inheritance. For the first 4 decades of the 20th century, the keywords were mutation and genes, the supposed units of inheritance. Mutation involved processes that acted on genes to bring about evolution. The period is also notable for numerous attempts to account for evolution through processes involving creatures as wholes, dismissed in the modern period as varieties of vitalism. In 1930, the heyday of mutation, appeared a book that, by combining mutation with Darwin's long-overlooked mechanism of natural selection, became inspiration for the modern synthesis, published in 1942, and for how we think about evolution today. My review. The Genetical Theory of Natural Selection by Ronald Fisher, 1930. Fisher's book is still referred to as the basis for the population statistics on which rests today's reigning theory of evolution, the modern synthesis. As recently as 2010, Fisher was given Richard Dawkins' choice as the greatest biologist since Darwin. He therefore could be said to have provided researchers in biology and medicine with their most important research tools, as well as with the modern version of biology's central theorem. But a quick skim through Fisher's book contents page raises a disquieting issue. Roughly halfway through come possibly token chapters on sexual selection and mimicry. Leading up to them are 6 chapters on genetic theory. Following after them come 5 chapters on eugenics. Given that this book was published in the heyday of eugenics in 1930, the theory arrived at in its first half can be suspected of being intended primarily to provide a more impressive theoretical basis for the eugenics in its second half. Of the theory to be developed, Fisher writes, neither its logical cogency nor its important to sociological theory seem to have been ever widely grasped, and apart from a few ephemeral papers of my own, and a brief discussion in Major Darwin's recent book, The Need for Eugenic Reform, it might be said to have been totally neglected. Given that slant to the book, I think the reasoning presented in it deserves a critical examination that I doubt it's getting, judging by how hard the book is to find. No copy was available on interlibrary loans, and readers advised against purchase of the only available reprint of the original edition. I bought a copy of the 1958 revised Dover edition to review. Now, I'm not the one to do so. I have no training in or talent for statistics. All I can do is cast a generally skeptical eye on the assumptions made and see if they pass muster. What I approached the book wanting to know is, does this book succeed in making Fisher's new focus, how chromosomes accumulate damage, along with Darwin's natural selection, a reasonable candidate for our primary theory of evolution, as it is said to? I concluded, no. The key issue Fisher addresses is variation. For natural selection to work, it has to be kept supplied with new variations. Darwin seems to have taken it for granted that new variations would automatically pop up, all of them as viable as the ways existing creatures already varied. Then, as the environment changed, some of those old ways might not work as well as some of the new ways, leading to those new ways being selected and appearing more frequently in future generations. Given sufficient time, as the environment continued to change, enough new variations would come along, get selected, and be passed on for creatures with these new variations to qualify as new species. For a while, Darwin's mechanism met with the approval of his peers. But after his death, the focus began to shift from selection to variation. If streams of such new variations are guaranteed, as Darwin seems to have assumed, how was his theory different from that of Robert Chambers in Vestiges of the Natural History of Creation, published 15 years earlier? Chambers had supposed the specifications of all living and future species of creatures had been embedded by God in the original embryo, already in place for changed environments to elicit. Where else could Darwin's variations come from, if not from God having already embedded them in the embryo in anticipation of the right conditions eventually coming along to select for them? Livestock breeders, meanwhile, were having the opposite problem. Having selected intensively for just the ideal mix of variations in their livestock, they weren't seeing any new variations coming into existence among which they could continue to select. And if new variations did not spontaneously occur, Darwin's theory of natural selection fell apart. Fisher began by identifying a new source of variation in the new science of genetics. That an independent study of natural selection is now possible is principally due to the great advance which our generation has seen in the science of genetics. It has often been remarked, and truly, that without mutation, evolutionary progress, whatever direction it may take, will ultimately come to a standstill for lack of further possible improvements. It had become apparent that inheritance involved long molecules in the nuclei of cells. Mutation referred to changes in genes, information coded for along those molecules corresponding to ways new species could arise. Fisher extended that term, mutations, to refer to damage that such large molecules are subject to, both from everyday physical decay and, in their case, from mishaps during reproduction. In place of Darwin's assumption that new variations had to come already viable enough to stand in for existing variations, Fisher proposed it could come in the form of such damage. The challenge then facing him was explaining how damage like that could serve as a suitable source of variation for Darwin's natural selection to work on. The key proposal Fisher came up with was, very occasionally, just by the laws of chance, instances of this damage to our genes were bound to be improvements. To these imagined improvements that he conjured up by appeals to logic and the laws of chance, he gave the name beneficial mutations. Beneficial mutations, he suggested, are the variations natural selection selects for to bring about the evolution of new species, and given a sufficiently promising stream of beneficial mutations, the evolution of new orders, even kingdoms. But of course there's a problem. As Fisher admitted, in every generation, harmful mutations will be in the great majority. Note that, in the great majority. How can natural selection turn that great majority of harmful mutations into a preponderance of the few that are beneficial, resulting in an overall increase of fitness? Here, if my analysis is correct, Fisher makes a critical omission. He does provide equations showing that, given the action of natural selection, beneficial mutations will over time exponentially increase and harmful mutations will decrease. But he nowhere comes up with an equation that tracks the effects on fitness over time of both these two kinds of mutations together, with variables expressing how greatly harmful mutations outnumber those that are beneficial. Doing so would, it seems to me, be bound to reveal an ever-increasing and overwhelming influence of the harmful mutations, leading to a rapid decline in fitness. For natural selection to eliminate all harmful mutations while sparing all the beneficial mutations, as he supposed, natural selection would have to be 100% efficient. But Fisher gives natural selection an efficiency of only 1%. A process only 1% efficient can't entirely eliminate a great preponderance of harmful mutations while sparing all the few that are beneficial. The result can only be the great majority of harmful genes accumulating just a little more slowly, and beneficial genes increasing just a little more rapidly. But this can have very little effect on their combined action. The outcome is bound to remain a very rapid surplus of harmful genes and quick decline into extinction. Let's look at details of his work. First, the concept on which the whole of the modern theory of evolution exists, the beneficial mutation. Fisher brought it into existence by surmising, in addition to the defective mutations which by their conspicuousness attract attention, we may reasonably suppose that other, less obvious mutations are occurring, which, at least in certain surroundings or in certain combinations, might prove themselves to be beneficial. That's it. All justifications for use of the concept, both by Fisher and all later advocates of the modern theory of evolution, rest on his use of the phrase, "we may reasonably suppose." He doesn't explain why beneficial genes will attract less attention than the more apparent harmful mutations. To me, that sounds like an excuse for why they had not been observed. Are they likely to ever be observed? It would require an enormous number of experimental animals and extremely precise methods of experimentation to demonstrate so small an effect experimentally. In other words, no. We are to take on trust the genetic basis for evolution, some damage to genes being beneficial as Fisher conceived it. Second, his estimate of the efficiency of natural selection. He consistently refers to it as having a value of 1%. Here's a couple of examples. It will be readily understood that if we speak of a selective advantage of 1%, with the meaning that animals bearing one gene have an expectation of offspring with only 1% greater than those bearing its allelomorph, the selection advantage in question will be a very minute one. If we confine attention to mutations possessing a selective advantage of just 1%, and he goes on, while assuming natural selection had such little efficiency, 1%, Fisher at the same time claims it can reverse the preponderance of a great majority of harmful mutations into a preponderance of occasionally beneficial mutations. Throughout, Fisher reiterates how he sees natural selection increasing overall fitness, against the action of natural selection in constantly increasing the fitness of every organization. And in order to consider in outline the consequences to the organic world of the progressive increase of fitness in each species of organism, so on. In the following example, he even contrasts his mechanism for evolution, which appears to decrease entropy, to the increase in entropy otherwise prevailing throughout the universe. It will be noticed that the fundamental theorem proved above bears some remarkable resemblances to the second law of thermodynamics. Both are properties of populations or aggregates, true irrespective of the nature of the units which compose them. Both are statistical laws. Each requires the constant increase of a measurable quantity, in the one case the entropy of the physical system, and in the other the fitness of a biological population. Shouldn't his proposal's disagreement with the second law of thermodynamics have given him pause? If I am right, and Fisher's invoking of genetic mutations fails to provide natural selection with the variation it needs, how did it get made the foundation for today's scientific mechanism of evolution? First, no one reads his book. You can tell that from it not being kept in print by the original publishers. Second, I believe it is generally assumed that evolution, the modern synthesis, the book that gave its name to the modern scientific theory, drew heavily on Fisher's work. In fact, the book barely refers to it. Third, as the author of the statistical standard by which the validity of all scientific findings are judged, recall Richard Dawkins' reference to Fisher as having provided researchers in biology and medicine with their most important research tools. Fisher is beyond challenge. The one mathematician I presented the book to check my suspicions backed away as being, if asked, to walk over hot coals. You don't challenge the master. He may be the master of mathematicians, but if I'm right, then Fisher's fudging, in order to give eugenics a more impressive basis, will come to stand as perhaps the greatest scandal in all of science, both for its baleful influence on science and for the support it gives to physicalists' advocacy of physical determination and dismissal of free will. At least all the opinions expressed in the books on the modern synthesis are thrown into question. Concerning Fisher's well-known predilection for eugenics, I end with this. Numerous investigations have shown that the birth rate is much higher in the poorer than in the more prosperous classes, and that this difference has been increasing in recent generations. The type of man selected as an ancestor of future generation is he whose probability is least of winning admiration or awards for useful services to the society to which he belongs. The composition of existing populations, graded both in social ability and in effective fertility, presents special and much graver difficulties, which only a people capable of deliberate and intentional policy could hope to overcome. So are you impressed by this foundation document of the modern synthesis?